Yeah, once again, thank you very much for the introduction, and also thank you, Cohere Labs, for inviting us. It's a pleasure. We're honored to present our work, DenseMarks. Our work is about learning canonical embeddings for human heads, and it's been done jointly by Dmitrii, who is also today in the call and will be talking about our paper, Alexei Artemov, Ananta Khatarai, and me. Let me start on the presentation of our work. Anyone who has ever worked with the tasks of face tracking or head tracking probably is acquainted with the notion of face landmarks. These are characteristic points on the face which define the locations that are easy to see. For example, you can see some of the points on the left here, and some of the points define the corners of the eye, some of them define the points on the eyebrow, on the nose, on the mouth, and so on. And these points are a crucial step in face tracking. They are already around for 20 years or more, and they are widely used in various applications of tracking of human faces and heads. For instance, for head avatars, which mainly constitute the task of reconstructing an avatar of a person from a single camera, which watches the person, or as in this example of Apple persona avatars, it could be a constellation of images from several cameras within VR headset. Face tracking
Artem, I think so. You have stopped your screen sharing.
Okay, that's weird. Check. Can you see it now?
Sharing is off. Okay.
Can you see it now? All right.
Can some move this if you want. Okay. Yeah.
All right. As I've been saying, face tracking is widely used in head avatars as well as in other applications such as face masks, widely used in cinema and entertainment, where you need to alter a part of the face or hair or some other parts like neck or clothes, or add accessories. And yeah, since these face landmarks are around for a long time, they've been quite widely used to make the first step, the first order approximation of the face. And how it's usually done is you have a face parametric model, so a face template, and if you'd like to align it to the face in the image, you first align it to these predefined locations, the landmarks, and then you do some small adjustments like using photometricals or something similar. And even though it was pretty much enough before for reflecting the faces, today when you need to create something more complicated like head avatars, this is sometimes not enough. And I'm going to show you an example. So this is a real example of using some off-the-shelf head tracker, and it's using these face landmarks shown as yellow circles on the right. And you can see that most of the time the parametric model fits the face pretty well, but if we talk about the rest of the head, like the scalp and the ears, they can be misaligned. So you can see if it is a bit wrong at the top, and then at the bottom the fit is a bit better, because at the top we are missing information about the rest of the head, such as these landmarks that are missing in a set of landmarks that are widely used. So if we had these landmarks at our disposal, we could probably fit the head a bit better. Some solutions based on landmark estimation, such as, for example, MediaPipe, involve estimating more landmarks, but as you can see here, these landmarks are still concentrated on the face region, so they don't anyhow help tracking the complete head. When we were thinking about this problem, we thought maybe we could improve the head tracking by simply annotating more landmarks. So how it's usually done, how these face landmarks are trained, is someone asks human annotators to annotate lots of images by handpicking with the mouse the landmark locations. And we thought, okay, can we just hire lots of annotators and ask them to find more landmarks on the head? And the answer to this is twofold. It's yes and no. So on the one hand, one can annotate some landmarks that are really easy to see, like, for example, the upper point of the ear, the lower point of the ear, and so on. These landmarks are pretty easy to see, and if you ask anyone can potentially annotate them. However, some other landmarks are a bit harder to define. So if you look, for example, at these points, it's always a question, how do you define the points on the hair? It's a bit ambiguous, and I presume every annotator would annotate them somehow differently, especially given that hair can be different. The neck is also a problematic region, as you can see down below. The points on the neck are really hard to define because the surface is just monotonous. Due to this, I think landmark detection approaches have not really been prospering, apart from the face landmarks. And if we look at other bodies of work, there is a famous branch of prior art concentrated on dense representations. So the famous approach is DensePose. It's a paper from Meta or Facebook back in the day, published in 2018, and this one involves learning a dense representation based on correspondences which come from a parametric model of the full body. It's called SMPL. So if any of you have worked with full body tracking or similar tasks, you probably heard about SMPL. It's a parametric model which includes a template for the full body, so only for the skin, no hair, no clothes, nothing. And this DensePose method is about regressing the UV locations on this parametric model template. And a few works down the line, there's been Body Map, also published by Meta in 2022. And this one is an extension of DensePose to seamless landmarks. So DensePose try to predict UV coordinates which have seams, and Body Map predicts something continuously three-dimensional. So yeah, did my sharing stuff again?
Yeah.
Something weird. Right. Both of these approaches and many others have still exhibit the same problem, that they intend to estimate embeddings for the part which is covered by the parametric model of the full body, but for many other regions like hair, which is not covered, they just cannot predict anything. So in other words, they do not work with regions which are harder to define. So in our method, we try to find a dense representation which is more complete. And by this, we mean that we do not use any parametric model correspondences. Instead, we try to learn the embeddings fully unsupervised. And what do we mean by that is the observation that if we have a few views from the same person from different viewpoints or in different expressions, it is only enough to know for some of the points where they match on the other view. In more detail, we take a collection of token heads videos. There are many datasets available now publicly, such as Settled VHQ dataset, which we used. And these datasets contain videos of interview style, like TED Talks or something similar. And we take a state-of-the-art point tracker and ask it to annotate the points along the course of the video. So if you look, for example, here's one of the videos from this dataset we used, and we just allocate a bunch of points in the first frame, and then we ask the point tracker to keep track of those. And now if we take any arbitrary pair of points, a pair of frames in the video, we would have a point in the first frame and a corresponding point in the other frame. This will give us the supervision. And the other component which enables learning is shared canonical space. So even though we in the dataset we have only videos where each video is of the same person, and so supervision is only coming from pairs of frames of the same person, we use canonical space, which bottlenecks the network to project every image into the same space. And this is an inherent assumption for the network that every face could be seen as a realization in the same canonical space. Now Dmitrii hopefully will take over and talk about the method part. Not sure Dmitrii is in the call. I saw him popping up and out. Yep, I think he's not. Maybe let me take over in this case. Give me a second.
I think his internet was having a couple of issues because he kept joining and leaving.
Yeah, I saw the same. So that's why I'm wondering if he will be able to join. If you give me maybe a minute, I'll try to open his part of the slides, and maybe I'll continue presenting when, if he's here, he could take over. All right, let me share my screen once again. Can you see it? All right. So now if we proceed to the actual method, DenseMarks is structured roughly like this. So we have an image, which we transform using some network, which we call the embedder, into a map where every pixel is exactly aligned with the image pixel, the corresponding image pixel. And here in the output of the network, each pixel contains a three-dimensional embedding. So you can see the shape is the same as the input. But this embedding is not just random. This embedding actually corresponds to a location in the cube. So this cube is a canonical space, which is interpretable. This means that regions are distinct in the space. It is queryable. So it means that you can pick a point in the space, in the canonical space, and you'll be able to trace this point back to the image. And you know what kind of the point it is because the space, the image of the point of the sample in the space kind of resembles the head. So you'll be able to find the point that you want. And it is smooth because similar points on the head surface correspond to close points in the canonical space. To train our method, we used SetupVHQ dataset, which consists of a bunch of videos, 35K videos namely, and we run one of the state-of-the-art point trackers, namely Code Tracking 3. And this way we get around 300 tracks per video that are being maintained. So 300 means that we start with a bunch of points, but then sometimes tracker fails and it just cannot estimate the whole track. And that's why we only count the tracks which we have in full. And this dataset features, even though it features mostly frontal images, you can see like something with the sharing again, I suppose. You can see even though this dataset mostly contains close to frontal images, you can see that sometimes images are more profile view. And yeah, the point tracks estimated by Code Tracker look kind of like this. So you can see they're also estimated for the hair, for accessories, and the neck and other parts. If we talk about the training strategy, we take our method, which consists of the image embedder and the embeddings estimation, and these embeddings represent the locations in the cube. How we train this method is we train it not in single images, but in pairs. So we apply this embedder in a Siamese fashion, and we predict those embeddings for 2 frames of the same video. So you can see it's the same person here and there, and we always pick 2 random frames from a sample video. So the network in 2 branches always sees the same person. And yeah, we estimate embeddings for those 2 images. And how we train it mainly is we use contrastive loss. So we use the points which point tracker found. So I remind you that we have point tracks for the whole video. And this means that we can take a bunch of points in the first frame and we'll be able to find the corresponding points in the second frame. So how contrastive loss works exactly is if you look at these points, so we have 3 of them here, just for an example, but we actually have more of them. So here it's only 3 for simplicity of the explanation. We take the embeddings estimated by the network for these points. So for the first image, they are feature 1, and for the second, they are feature 2. And we calculate a gram matrix. So gram matrix is this matrix M, and in every cell, it's a dot product of the corresponding feature here and there. So what it means more intuitively is we calculate dot product of embeddings. If it's on the diagonal of the matrix, it means we calculate dot product of the matching points. If it's outside the diagonal, we calculate a dot product between the point and the other point, which is not mentioned in this one. And now what we want to achieve is we want to ensure matching, and contrastive loss ensures that positive pairs attain the same embeddings, and negative pairs, so pairs of not matching points, attain different embeddings. And how do we achieve this? Is we try to minimize the difference between the gram matrix and the identity matrix, as shown here. So the closer we are to the identity matrix, the better. And what it means is dot product should be closer to 1 for positive pairs, and it should be as close as possible to 0 for negative pairs. Okay. So hope it's roughly clear. And one technicality about this contrastive loss is it's very hard to optimize for three-dimensional embeddings. So if you look back here, the embeddings we have, these vectors stored in every pixel, are three-dimensional, and this means that when we calculate the dot product in the contrastive loss, dot product in the three-dimensional space corresponds to the angle between vectors, right? So when we say we want the dot product to be as close to 0 as possible, it means we want the vectors to be perpendicular, right? And in three-dimensional space, if you take a 100 by 100 dimensional gram matrix, so 100 points versus 100 points, it's almost impossible to ensure that 100 points are roughly that one point is roughly perpendicular to 99 other points. So in three-dimensional space, it's impossible to find 100 mutually perpendicular vectors. But the trick is, in higher dimensional space, it is actually possible because of the curse of dimensionality. So if you take a higher dimensional space, you can find many more vectors that are almost perpendicular to each other. And this number of vectors you can take grows exponentially. So this means that we can apply this trick. And if we store a highly dimensional feature in every location of the cube, then what we can do is we interpolate this feature. So if we ended up in some location in the cube, we can interpolate it between the neighbors. And this way we get a map of embeddings, which is much more higher dimensional. Namely, we used 16-dimensional embeddings in our work, but any number could be used. And this map would still be exactly aligned with the input image or with this embeddings map, but it's not going to be H1W by 3, it's going to be H1W by 16. Okay. So, and now we apply the same contrastive loss. And this contrastive loss doesn't suffer from the issue with perpendicularity of the vectors. So that's why this way it's much easier to train the method. Another thing we have to talk about is, you may be wondering, like, if we just take this method and it might learn any kind of a space. So there is basically there is basically nothing that restricts the space to be like you see it here. So the network, it's an ill-posed problem, right? The network can learn any kind of a space. It could learn a fully rotated space, right? It could learn a zoomed-in space, zoomed out, tilted. We could basically see anything there. So there is no constraints that make the space aligned and look like a head. Okay. So when we thought about this, we decided to add two regularizations. So one loss which helps learn a consistent space is segmentation loss. So segmentation loss operates on the semantic features. It's just a single convolution, and it operates as a regularizer that makes sure that the regions in the canonical space would be in the right places. And another regularization is landmark loss. It compares landmarks estimated for an image and hard-coded anchored landmarks in the canonical space. So this way we actually ensure that the landmarks end up in the right locations. All right, so that was it for the method, and let me maybe talk a bit about the applications and benchmarks. So, but first of all, let me describe the baselines. So, when we compare our method to others, we mainly look at what is today called foundational models. So very big transformers that are trained for features, trained to provide great features. The first one we consider is Sapiens. It's a model from Meta that is trained for depth and normal estimation of human head images. So it's trained on humans, which is the same domain as ours. And the features we can extract from the pre-trained version of the model is they have pretty large dimensions, so more than 1,000. The other two shown here are generic foundational models. So DynaV3, I guess many of you heard of. It's a recently released version of Dyna foundational model trained on category unspecific images and hyperfeeds or diffusion hyperfeatures. This was a method also for feature learning based on distillation of features from a pre-trained stable diffusion. The first benchmark we consider is point querying. So here we compare our method to these three baselines that we just described, and what you can take a look here at is the semantic location of the points. So here we have 5 sample points that we found in the canonical space by manually picking them, and you can see the description below. And if you compare them to other baselines, so for instance, Sapiens does quite a lot of mistakes with these points, likely because the embeddings are very highly dimensional. Hyperfeatures and Dyna do a better job, but they still do mistakes sometimes. So, for instance, there are some mistakes related to symmetry of the face. So, for example, the green point is a right ear, and hyperfeatures found it correctly, but Dyna was probably attracted to the left ear instead. And yeah, so you can see some issues with the orange point and so on. And here's another example. So with facial accessories or head accessories, the problem becomes a bit harder, but our method can tackle it because in the training data we had quite a lot of those examples. And the point tracker could track the points along the course of the video. So for our method, it's not such a big problem as for the other methods. So for example, if you look at the forehead center in the bottom row, then all of the baselines fail, but our methods finds the forehead center successfully. Here's another benchmark. This was just a toy test where we handpicked a point in the canonical space, and we defined a sphere around it, and we projected the sphere onto various images. And what you can see here is we found the point by hand, so we expected this point to be in the location which is defined in the captions below, and the region is consistent. So you can see that if we define a sphere around the point, then the sphere projects onto the points near this point in the image space, and it represents to some extent consistent regions. And if one would define a sphere but more precise region, we would probably have more accurate borders, not as mushy as here. This benchmark is focused on warping, so this is a pretty standard thing when people evaluate feature extractors. And what is happening here is we evaluate as to whether it is possible to warp pixels from source to target using only DenseMarks features. So we estimate DenseMarks features for this image, for that image, and then we find for each pixel in the target frame, we find the nearest neighbor in the source frame, and we just copy paste it there. You can also look at the top row. So top row represents blend of the RGB with coordinates similar to mesh grid style. So we basically define mesh grid here, and the warp is good only if the colors are consistent. So if you look at the resulting coordinates, then if you have, for example, a red color here, then it should be coming from the region which is red in the source image and the corresponding mesh grid visualization of the coordinates. So basically what we intuitively expect in this benchmark is that it's going to do kind of a face swap. So the face from here should be swapped onto there. And the same should happen for hair and neck and clothes, ideally. Okay, and here's a comparison to the baselines. So source and target are defined in the left 2 columns, and you have the same 3 baselines defined before in our method. So if you look at these images, first of all, I think what looks the best is Sapiens from the first glance. So it's the most resembling the target person, but I have to note that it's actually contrary to what we would want to expect, because we expect kind of a face swap, right? We expect swap the face to be swapped from source target. And you will look at the coordinates that Sapiens produces, then these coordinates are a bit unexpected. So I think what it does, it kind of tries to find the same color in the source image as for the corresponding pixel in the target image. Like a very good example is the beard. So if you look at the beard, it is black because it took these points from here, from the beard. So that's a pretty unnatural face swap. But if you look at the three others, then they make more sense. I think Hyperfeatures and Dino make a very good job, but they still somehow suffer from some artifacts or lack of smoothness. And here's another example. So you can see that all the methods don't produce a perfect result. Our method as well, so it doesn't produce the perfect hair, but it does its job in the sense that it tries to swap the face and hair from here to there. And because we don't see a lot of hair in the source image, the only thing it can do is just to shrink it. And that's why we have a blurry region here. Another benchmark or maybe even application of our method is head reconstruction or multi-view stereo. So what we considered here is if we take a bunch of images, can we lift them into 3D using only DenseMarks embeddings and camera poses? And for this, we took NeurSample dataset. So the images you can see here are from NeurSample dataset. And this task is usually solved by methods like structure for motion and multi-view stereo. So if we have camera poses, it is multi-view stereo, and this is often based on techniques from classical computer vision, like a point feature extractors like SIFT or SURF or something like this. And the classical toolkit for this is ColMap. If any of you work with 3D, you've probably heard of it. So ColMap is a classical Swiss knife tool for this. And recently there's been a lot of prior art of works that don't require camera poses, like for example Master or Duster. So here is a sample from Master, and you can see that it does a pretty good job of reconstructing the head, but sometimes it misses some things, like for example flatter nose and real nose or wrong head shape. And our idea was, since our embeddings are pretty good, couldn't we just try to triangulate, so to lift the points only by looking at these images and their DenseMarks? Actually only at their DenseMarks, not even looking at the RGB. And yeah, here we test how it works with 2, 3, and 5 views. And what we do is we first infer DenseMarks maps for all of these images, and then we do triangulation. And this is what we obtain. So the triangulation here is done on CPU, so we don't require any GPU anymore. And it's done only within a few seconds on the CPU, and on GPU to be even faster. But for the sake of an example, it's not really important, I think. So here we see that it's possible to reconstruct 3D by only looking at DenseMarks embeddings, which proves that they're somehow semantic and they correspond to the semantic matching between points. So if we do the multi-view stereo, then the algorithm picks up the matching embeddings in separate frames and is able to triangulate the 3D location of the corresponding points. Here's another example. And this example is a bit more tricky because of the long hair. Another application of the method is head tracking, and I would say this is even a central application of our method because this was the original motivation. The head tracking algorithms usually involve estimating a parametric model. What is a parametric model? It is a model which can be controlled by parameters. So if you look at this, it's usually a fixed template, fixed 3D mesh, which can be deformed, and deformation is defined by several feature vectors. So shape defines the identity of the subject, so the shape of the head. The expression defines the face expression, the mimics. The pose defines the relative location of the jaws and the neck and the head itself with respect to the neck, as well as the global pose, which is the location of the head in the world space. And the color defines the appearance and texture. And how typical head tracking algorithms work is they take a video and they try to estimate the parameters of this parametric model, so shape, expression, pose, color, in every frame, and they keep some sort of consistency, so they try not to deviate from the previous frame estimation. So you can see an example here. This is from one of the state-of-the-art head trackers based on this parametric model called Flame, and they usually do it by mainly using place landmarks, which are, as we already know, not complete source of supervision for head tracking, and some other techniques like photometric loss. So we thought, why not try DenseMarks? And we could use it as a plug-in addition to a state-of-the-art tracker. So in addition to sparse landmarks, here we use DenseMarks for head alignment. And we found that for monocular videos, it oftentimes improves the results. So you can take a look at the comparison here. So in the top row, we have the results of the same head tracker as I described before. And in the bottom row, we have head tracker plus DenseMarks. And you can see that it performs better when it comes to swift rotations of the head. The same is observed here. So when the rotation is especially extreme, like here, and fast, then you can see the head tracker to fail. You can expect head tracker to fail, and DenseMarks makes it a bit more robust. Another application of our method is head pose estimation. So what is usually meant by head pose is how head is located in the world space. And by this, I mean the rigid transformation. So you can look at the head, you can see head as a deformable thing. So it has many axes of rotation, but here I mean mainly the rigid axis. So the head, if you consider it a non-deformable object, then you can rotate it and translate it into space, and the basis vectors of this rotation translation will be considered the head pose. And where head pose is usually used is, for example, for gaze estimation, or in the same applications of avatars or face masks. So if you, for example, download Snapchat and you'd like to add a face mask to your face, then you'll probably need some kind of a head pose estimation because you'll need to know where the person is looking. Yeah, and here we didn't try to outperform the baselines. It was more like a toy experiment. But what we found is if we take a look at the quality of head pose estimation from a pure RGB by a network like MobileNet, so it's a relatively lightweight network, then the error is pretty high despite the network being still quite capable. So it has many layers. And if we just replace RGB with DenseMarks map, then the same MobileNet starts performing much better, around 3 times better by the error in degrees of estimation. And here we also compare to the 6D RepNet, which is one of the state-of-the-art methods, just to give you the reference of the best error in the same dataset that people have achieved. As one of the nice advantages of our method, we also found that the network is very robust, probably because of the training dataset. We made a few images. So this is Dmitrii, who unfortunately couldn't join the call and present, but we have him here. So the images taken in different lighting conditions still work for DenseMarks, and the embeddings still work for DenseMarking. So you can see the result is pretty good. Here we apply DenseMarking from source to target, and we get the worked result, which very much resembles the potential face swap. So I think it resembles pretty much the same person in the lighting conditions of the source image. So this can be seen as another application of the method, or as another proof of its robustness. Here we make an ablation study. So if you remember, I mentioned these 2 regularizations, landmark loss and segmentation loss, which help making the space interpretable and static. And we show that if we disable those, then, for example, region find becomes more problematic. And you can see, especially if you consider the forehead center region without landmark loss, then it becomes too small, or the ear region. Another ablation is focused on removing the canonical space. So what happens if we take our method and instead of using this bottleneck, we actually try to predict the final features directly, which are highly dimensional. So this will be much simpler, right? we would like to see what happens in this case. Potentially, this could be used. The only obvious downside is that we lose the perks of canonical space, which is the ability to query it, the interpretability, so you can no longer find a point or region in the space and project it on the image, but still for example, for DenseMarks, this could work. Maybe it gives better results. And we found that no, it doesn't. So both by the numbers and by the visual investigation. So you can see here the comparison of DenseMarks benchmark for our method, which is on the right, and the same method without using the canonical space. And you can see that, especially for head accessories, we can see lots of issues and also artifacts in the face region. Here we show the comparison, which we also show in the paper, and this is the comparison to all the baselines we used. So hyperfeeds or diffusion hyperfeatures in full and Dynamo3 and Sapiens I already covered. Here we have them grouped into two sets of rows. So the first set is generic models. Diffusion hyperfeatures and Dynamo3, they are trained on generic data. So they were not trained on faces specifically. And these four methods were trained on humans or on faces. So Farrell is a segmentation network, and we use its features. Sapiens I already covered. It's a network trained on humans. Consistent service embeddings, or CSE in short, is another method trained on humans, but a bit older one than Sapiens. And we include an additional more like an ablation, but it worked pretty well, so we consider it a baseline. This is where we took Dynamo3 and we fine-tuned it on the same dataset as ours, which is dataset of human heads, and you can see it improves better than the original Dynamo3, but still worse than our method. So there is still a quality gap by all the metrics, even with respect to the even with respect to the best baseline. Here's a pretty interesting set of ablations. So in the first ablation, we check if we can remove a bunch of tracks. So by tracks, we mean the point tracks estimated by the point tracker, and we were wondering if it's possible to remove some of those tracks to see how sensitive the method is to having a lot of tracks in the data. So would it still work if for each video in the training we have only a fraction of the tracks? And it turns out it does. So it does even if we take 10 times fewer tracks, the quality doesn't degrade that much. So you can see that the quality gap is significant, but it's still much better than the best of the baselines shown here for the reference. And the other set of ablations is related to the noise addition. So here we try to add noise to the tracks in the ground truth to estimate again how sensitive it is to the tracks. Here, not to how many tracks we have, but how accurate they are. And even for the noise of 16 pixels, which is a very large noise, the method still works. There is significant quality, but it's again still better than the best of the baselines. If we talk a bit about the future work, we hope that the same method could be applied in different domains, and we did a toy experiment where we applied in chairs. And here we took correspondences from the dataset that already contains those, and we found that the method works, as shown here. And another potential direction of the improvement is related to improving robustness of the method. So we can still find some videos which are extremely challenging, like here when the person occupies a very small fraction of the frame, or the head pose is very challenging because in the data we didn't have images of the back of the head, or almost didn't have, and that's why if the angle is very unusual for the method, then it can fail. Still, despite that, you can see that the method is still better than the baseline, which sometimes completely wrongly estimates the head position, but the head shape is also not correctly estimated, so there is a room for improvement. Thank you very much for listening, and thank you again Cohere Labs for inviting us. Here we invite you to check out our project page, so you can scan the QR code here. And yeah, thank you for listening again, and we welcome your questions.
Awesome. Thank you for your excellent presentation, Artem. I would like to begin by asking a query about the different depictions that you presented. One like for the head pose estimation, and like you were tracking according to the the 3 dimensions, and like where do you see like just not the head, but from the gaze perspective too, like combining that, and whatever you see, you kind of like have a object that describes in the uh, uh, I mean to say in the background, that that you have a 3D or depth estimation of. So like I was trying to bring towards a holistic picture of like you are looking at the monitor and you get a holistic view of the depth that you have between your eyes and your monitor as well. So like, do you have any ideas or any recommendations of that sort of work?
Right. So I think gaze estimation, we haven't tried it directly. So there are methods and benchmarks for gaze estimation where a neural network just takes a look at the image and tries to understand where the eye pupil is looking exactly. And yeah, we haven't tried this application with DenseMarks. I think it might work, even though it might be a bit problematic because it wasn't trained for this task, and also we don't know how well it maps the eye interior to the canonical space. When we talk about the depth estimation, I think it's also part of your question, right? So how do we estimate the depth from, for example, single web camera? I think it is indeed possible, and maybe not directly possible using this multi-view stereo benchmark, because there we need at least 2 images from different viewpoints, and in the webcam case, we have only one viewpoint. But with the webcam stream, we also have a bunch of frames. So we can, for example, wait 1 minute and we can ask the person to do the rotation of the head like this, right, left and right, top and bottom, and so on, which would give us different views. And I think there DenseMarks could be useful to do the mapping. So because correspondences are important for fitting the avatar, right? There are a bunch of methods for estimating the human avatars from this kind of data. For example, NeurFace paper from I think 2020 or 2021, I'm not sure exactly. And there's been also a stream of works that is focused on the same. So we could potentially just use DenseMarks there as a drop-in addition or drop-in replacement for something that involves alignment of the faces. Usually those methods also use facial marks to align the face, and they have the same issues. So DenseMarks could be used instead. Or it could be also used, for example, to directly map the colors into the canonical space and then work in the same space. So this way you could basically map all the images into the same space, and then you can work in there. So I think that's only if you could
yeah, like it's a
so,
yeah, I think so. Your meat is like disconnecting, and like you're skipping some of the words there, but like I get the gist here. And like I would like to like invite Benedict and others to ask a few queries here. I think so Benedict's meet has also okay. Yeah, this kind of issues I think so are common today. But anyways, this was a awesome presentation, and like in the end, and I would like to ask you about the work that you do at Apple right now. So is it like confidential or like under the wraps totally, or can you discuss something about that, or is it related to your 3D dense mapping like work that you have done earlier?
Yeah, so I worked at Apple Munich Vision Lab, which is in part focused on human avatars, but unfortunately the work we do is confidential fully, so I wouldn't be able to share it. You can look out for the releases from Apple, and at some point if there is a release, then this would likely be related to what we do.
Okay, cool. Yeah, with that, I think so we will end the presentation, and thank you for your awesome like end-to-end technical breakdown of the paper and the other
Okay.
things. Yeah.
Thank you very much. And yeah, thank you everyone for listening. I'm happy to keep in touch.
Thank you.